Hello, dear students. So here I'm continuing my session on the scale up of the fermentation process. So the next step is inoculum development and culture expansion. So let us start. So I guess, briefly told you about the master cell bank, which is the master stock of the cell line which you have been using for your desired metabolite. But this is the master stock and it has to be stored at liquid nitrogen, that is 196 degrees Celsius, or at minus 80 freezer, or even lyophilized. So this is a stable cell bank that ensures the consistent and predictable production in the long term. So from the master cell bank, you make the several working cell banks, which is used for the routine production. And if you follow this strategy, it will allow the original source of genetically stable master cell bank to be preserved for a longer period of time. Now, there are some general tasks of a cell bank. So, the cell recovery upon the freeze and then thawing, then you go for the growth test. So how the cells are growing, or what is the viability of the cells. Then you also perform the contamination or the purity test. So you plate the test in the desired agar media and see the colony morphology. Even you can use the genetic discrimination test and even phenotypic test. Then the next is the real-time stability testing. That means how much time it is taking for the growth. Is it the standard time it is taking, or it is growing slowly? Then the genetic stability of the organism, and how is the product it is forming, whether it is the same product or it is a variant of the product. Then product qualification, and we initially use a small scale production model to check whether this cell bank is suitable for the larger scale production or not. Then obviously you perform a comparability study of the MCB and the WCB to ensure that the WCB is working fine. Now there is a term called seed train scale up strategy, which is used for mainly the culture expansion from the smaller volume to the larger volumes. So let us see the wild thaw conditions. This includes the temperature at which it is being thawed and up to what time it is being thawed, and uh, what is the inoculation. How much is the inoculum? Then inoculation ratio. So how much inoculum needs to be added uh, with respect to the amount of total culture. So it is a volume percentage and it has to be defined at each step of your fermentation scale up. So for the microbes, usually it is 0.1 to 5%, which is used. And there is a seed train media as well. This media is basically optimized for the growth, but not the production of the metabolite. So they actually support the growth rather than the metabolite production. And the various genetic stability and the production stability testing is done during this culture expansion process or the seed train process. So there are some standard growth times for the revival of the cultures. Like for the lyophilized cultures, it takes about 4 to 10 days to revive it properly. For the frozen cultures of bacteria, it takes just 4 to 48 hours. Actinomycetes, including the mycobacterium, it takes 1 to 5 days. Then fungi, it takes 1 to 7 days. For the refrigerated cultures of bacteria, pretty fast, 4 to 24 hours. Actinomycetes, 1 to 3 days. Fungi, it is 1 to 5 days. Now, there is standard inoculum concentration as well we use for the bacteria. 0.1 to 3% for actinomycetes, it is 5 to 10%. For fungi, it is 5 to 10%. And for the spores, it is in the number of spores, 1 to 5 into 10 raised to power 5 spores per liter of culture solution. So that was about the inoculum development and the seed train scale-up strategy. Now the next is raw material and nutrient availability. So this I have already briefed you the raw materials which are used at the larger scales, the cheaper sources. So this I will just skip. Then coming towards the pH, yes, pH is very important. So pH needs to be tracked at all the scales of the fermentation because that is the key route for optimization. For example, here, this is a typical fermentation profile for the production of an antibiotic called chlortetracycline. So in this one, so you see this graph, there is the production of ammonia in the initial phase of the fermentation, and then it goes down. Then the pH simultaneously is rises because of the production of ammonia, and then it goes down and stabilizes at pH 7. So now you can see the metabolite, which is an antibiotic chlortetracycline in this case, will start producing only when the pH is stabilized. So you can see there is consistent production of the secondary metabolite, in this case chlortetracycline. So it is produced only after the pH is stabilized. So if you make sure the pH is around 7 in each scale-up plant, so you will end up getting the desired metabolite. Then coming towards the shear. So shearing is lower in the shake class as compared to the higher production plants, and it increases dramatically when it is scaled to the stir tank reactors. That means we are using the impellers, baffles for the optimal oxygen transfers or the gas transfers. So in the case of shake flask, you can increase the shear artificially by introducing either the baffles or the glass beads. Whereas in the large scale, like the stir tank reactors, you can use different agitators or impellers, different kinds like the disc impellers or agitators, the propellers and all. Also, you can use the baffles in the larger scale also, and you can control the speed of the agitators. So these are various blades. I have already mentioned you the disc turbine, curved disc turbine, blade turbine, tilted paddles, and the disperser. So the shear rates can also change during a fermentation. So when the fermentation is going on, at that time also the shear rates can change. For example, if the microorganism is such that it is producing a product which leads to the thickening of the whole fermentation media. So, for example, Xanthomonas campestris produces xanthine gum, which is a polymeric product. So, the shearing would be more in this case. Then, for example, it produces some enzymes. So, the other bacteria, on here it is the filamentous fungi, Cochlear bolus sativus. which degrade the viscous substrate, so producing the enzymes like pectinases. And in other cases, the morphology of the microorganism could change during the course of fermentation. Initially, for example, the microorganism is a pelleted form of growth, later it forms a filamentous form of growth. Like this one. Initially, it was the pelleted form and then it changes to filamentous. So it occurs mostly in the filamentous fungi or the actinomycetes group. Then comes the temperature maintenance. So as the scale up, because of the scale up, the volume increases, there is significant heat generation during the aeration and the agitation. So that has to be cooled down. So cooling can be increased either by using a jacketed vessel. That means you use a jacket, the cooling jacket with this yellow color, or use the internal cooling coil. So you can use this cooling coils, or you can heat your vessel in the open and spray it with water, which will cause the cooling. So you can keep the vessel outside in the air and spray it with water to reduce the temperature. Then comes the partial pressures. So in case of the larger fermenters, there is significant back pressure uh, because of the volume of the liquid present and towards the sterile envelope of the fermenter. Also, the hydrostatic pressure, because of the liquid present towards the base, is pretty high. So both these pressures will influence the partial pressures of the gases. For example, the partial pressure of oxygen as well as partial pressure of carbon dioxide. Usually the change in partial pressure of oxygen won't so much change the cell metabolism, but the change in partial pressure of carbon dioxide will have the inhibitory effect on the enzyme action and the membrane function, the basic metabolism of the cells. So it had, therefore, the partial pressure of CO2 needs to be monitored, which is being used, which is being done by the various sensors or the probes for monitoring the partial pressure of CO2 during fermentation. The last is the genetic changes in the population. So the number of generations a microorganism is passaged will increase the chances of the genetic variation or the mutations. So hence it is always advisable to use the inoculum developed from the working cell bank rather than using the other cultures which have undergone more passages or more number of replications. So to confirm, you can run a protein gel or a DNA level characterization of your inoculum or the starter microorganism at every stage of the scaling up to see that the fingerprint of the microorganism doesn't change. Okay, so there are various criteria for the scale up of bioreactors. So these all things needs to be constant, like the constant agitation, power input, then constant oxygen transfer coefficient, constant mixing time, constant agitation, impeller tip speed, or constant heat transfer rate, constant gas volumetric flow rate, constant gas superficial velocity. So let us first see the Reynolds number. Why are we studying it? Because this is a number which is arbitrarily used to see the turbulent flow of the liquid around the stirrers. How is the turbulence around the stirrers? So what is a turbulent flow? Turbulent flow is something like the two molecules of the liquid move in relation to each other, and that is called the turbulent flow. And this turbulent flow is characterized by this Reynolds number. So Reynolds number is designated either by Re or Nre, which is di square by into n into rho by eta. So di is the stirrer diameter and n is the stirring speed. Rho is the density of the medium and eta is the dynamic viscosity. So as I have told, the Reynolds number describes the flow of the liquid only at the periphery of the stirrer, not at the whole solution, but only at the periphery of the stirrer. So to distribute the turbulence homogeneously in the entire reactor, so you have to use an impeller of the appropriate shape and diameter. And the flow rate is crucial to the distribution of turbulence for proper mixing. So for example, here I am showing the Reynolds number of penicillin fermentation with Penicillium chrysogenum in the small and the large fermenter. If you use water in present in absence of a culture medium, so the water tends to have a more Reynolds number, that means more turbulence. And when you switch to a larger fermenter, it will even have a more turbulence. Then in case of the culture medium, the Reynolds number is lesser as compared to the water. And in the larger fermenter, it is more than the smaller fermenter. So this was about the Reynolds number to measure the turbulence in the liquid, mostly around the stirrers. Now let us see the power number, which is also called the Newton's number. So either it is denoted by Np or Ne. So it is a dimensionless parameter relating to the energy required by the stirring reactor. So how much energy or the power is needed by the stirring reactors. So it is calculated as imposed force upon inertial force. So P0 is the stirring power and N3 and N cube is the stirring speed into stirrer diameter is to power 5 into the density of the medium. So there is some correlation between the power number and the Reynolds number in the Newtonian solution for various impellers. So Newtonian solution means which follows the Newton's law of motion. So here you can see when in the laminar flow of mixing of mixing. So in this case, laminar flow means the flow is in just one direction. It is not the turbulent, but it is laminar flow. So in this case, the Reynolds number is, when the Reynolds number is less than 10, so there is a linear correlation between the power number and the Reynolds number. So the relation is Np is equal to power number is equal to K1 dot Reynolds number raised to power minus m. So the K1 is a constant dependent on the container geometry and the shape of the stirrer, but not dependent on the reactor size. And m is equal to 1 in this case. And in the laminar flow, the power required by the stirring is not dependent on the density but correlated with the fermentation parameters. So you can't find the rho, the density, but you can find the viscosity. So the power requirement in the laminar flow is nearly equal to n raised to power 2, which is a stirring speed, into diameter of the stirrer raised to power 3 into the dynamic viscosity. So when there is a turbulent flow of the mixing of liquid, and when the Reynolds number is greater than 10 raised to the power 4. So here you can see the Reynolds number is greater than 10 raised to the power 4. So in that case, the power number is independent of the Reynolds number and is constant. So you can see in this figure, so the power number is independent of the Reynolds number. Even if it is increasing, the power number is more or less constant. So these different lines in the graph shows the different kinds of impellers you have used. So under these conditions, the power required for stirring, which is P0, is independent of viscosity but dependent on the density. So P0 is equal to K1 dot N cube dot di raised to power 5 dot rho, which is the density. And when the power number or when the Reynolds number is between 10 to 10 raised to power 4. So between 10 to 10 raised to power 4, there is no direct relationship between power and the Reynolds number. So it is not a simple correlation, but it is a bit complex. And if you consider different kinds of impellers, so the disc impellers use more power as compared to the slanted blade or the marine propellers impellers. So there is also a relationship between power requirement by the aerated bioreactors and non-aerated bioreactors. So during aeration, so as the effective density of the gas liquid mixture is reduced, the power requirement will simultaneously decrease. So there is a correlation between the power requirement by the aerated bioreactor and the unaerated or non-aerated bioreactors. So PG, that means in case of the aerated bioreactor, is equal to K, which is a constant, into Pi, which is the requirement by the unaerated bioreactor, into stirring rate, into stirrer diameter cube, divided by the aeration rate raised to power 0.56, the whole upon 0.45. So this is all about my this topic. Thank you.